150 kilometers south of here.
Okay. Are you in Kolding or?
I'm in Aarhus.
Aarhus. Okay.
So. I think it's about time to start. The first speaker of this morning session will be Vahid Khosidi from Danfoss in Nordborg, Denmark. Will you please introduce yourself, and then we will let your slides go.
Yes.
Thank you.
Good morning, everyone. This is Vahid Khosidi. As I just mentioned, I'm from Danfoss, Refrigeration and Air Conditioning Controls. And today I'm going to present our work that we had in the context of multi-pack project. It's a project that was funded by European Union, Horizon 2020. And the work today is mainly focused on the compressor mass flow rate estimation using data-driven methods and analytical methods and the comparison of them. And also, this is in the part 2 we were going to have in the afternoon. My colleague is going to present the evaluation of ejector performance. So the project that we have been working on and the installation has been the CO2 transcritical system. It's been an integrated refrigeration, air conditioning, and with all together also with the heat recovery and heat pump functions. And the system that we had consists of several technologies that are state-of-the-art technologies of CO2, power compression, overfed evaporators, and ejector for pre-compression and liquid recirculation. And also we had functions of direct expansion cooling and dehumidification. It's worth mentioning that the data that we received from the supermarket were coming from 2 major sources, Danfoss Pack Control, that we had HAPC 782 and 781. And we had the data logger that was collecting data through separate physical sensors. So we had redundancy of sensors for more reliable data collection. And the sensors that we had were mostly temperature, pressure, power meter, and Coriolis mass flow meters. So as you can see here, we have M3 and M4 that is recording the mass flow through the evaporators. And we have M2 for the heat recovery mode. And we have direct expansion through M5 and M1 when we are getting liquid for air conditioning purpose from receiver directly. So the The methods that are common practice in mass flow rate estimation of compressors can be divided into these categories. The most common ones are energy balance, volumetric displacement, and manufacturer polynomials that are used. In energy balance, you simply take the enthalpy over the compressor, and you assume that you have a heat loss over the compressor, and then you calculate the energy balance. So that's one method. And the other method is based on volumetric displacement, and that means that you need to have efficiency, volumetric efficiency for the compressor, and then the mass flow rate can be estimated. There are also manufacturer polynomials that here we use the polynomials from Bitzer, and we have two operational conditions when running the system, that is subcritical and transcritical. And for both of these, we have separate formulas to calculate. And they are mostly based on pressure and condensing temperature. Data-driven method that was also used. We have several methods of using when we have a data and we are trying to do regression. And the two methods that we use and we got the best results were multivariable linear regression and Bayesian reach. So regarding data-driven method, first of all, why we use data-driven method? First of all, we had lack of mass flow meter measurement on the ejector ports. That's one issue. We didn't have mass flow through the IT compressors, and we had various operational modes that we were missing the information for ejectors because of that certain operation. These were mostly the reasons behind why we use data-driven. So when working with data, there are some steps that you need to go through, and it usually starts with cleaning data. As I mentioned earlier, we had two sources of data, and we had to merge them together and synchronize them together in a way that is usable. Then it comes to the correlation check. And the reason that we do a correlation check is that we want to remove highly correlated data. And that's usually the data that is unit converted. So when you get a data, there might be some pre-processing beforehand. And there are some unit conversions that you don't want to contaminate your data with the data that is duplicates. And that will also help you to know which are the data beforehand, to know which have the highest correlation. And then it comes the model selection. And in model selection, as I mentioned earlier, we had two methods used. And regarding the how the method is done, is that we have some analytical methods that give us good estimation of mass flow meters, as I mentioned earlier. And we can use those together with some other data that I will go through in next slide, and get the data prepared for training and testing the model. So we had a automated variable selection that we loop through all the variables. We train for a week, we test for another, and we test for other weeks. Just making sure that the model that we are training is based on real correlation and not just a fortunate event that we get a good match and a good score. Then at the end of this variable selection method, we check the score and we compare the results to see which variables are getting the best fit for our model. Looking into the LT compressors, what we've done for LT compressors, we have run through this variable selection, and we found out that the mass flow rate estimated based the variables that gave us the best fit were mass flow rate based on the energy balance, volumetric, and manufacturer polynomial, together with the power meters, and also the running capacity. So these were the variables which were giving the best fit, and adding or removing any of these variables would reduce the performance of the model in predicting the outcome. Regarding the empty compressors, we have repeated the same thing. And when comparing with the actual measurements from the field, we realized that there's only a few parameters, few analytical methods that are giving the good result. And from those, and it also can be seen from the trend, that the trend that is the energy balance method is following is pretty well matching. And the volumetric method and manufacturer polynomial method, they're not following the trend of the mass flow rate very well. And that brings us to the point why, when we are training the model, in the variables that are selected are not from the manufacturer polynomial or the volumetric method. Together with the energy mass flow rate from energy balance, we had power meters and suction pressure and suction temperature in the method. The comparison values of the comparison of the different methods bring us to the same point. Regarding the LT compressors, all the methods more or less give us a relatively good result, except the energy balance. And this indicates that the energy balance value, the energy loss value that we assume, can be usually overestimating the mass flow. So it's underestimating the heat loss, in other words. So we can see the similar process for the empty compressors, and we can see that the data-driven method gives a very good estimation also on the average weekly and also in the R square value. And finally, we have looked into the error to see how much the errors are bound. And we can see that the data-driven method is keeping within 10% for LT compressors. And even in the higher ranges, it's much more accurate because the absolute value. And then for empty compressors, it's mostly keeping within the 10% error range. So just to conclude everything together, we have looked into LT and empty compressor mass flow rate estimation, and it was proven for us that data-driven method has potentials to be used in further steps. And another next step we are developing a Modelica model together with Syntef. Thank you for your attention, and I also want to thank you, our partners and European Union, for funding the project.
Thank you very much, sir. And then we will turn to Slido to see if there's some questions. And it seems that there are no questions. I can perhaps ask a question myself. Many years ago, we did some measurements in Copenhagen area, and there we had 4 supermarkets in the same city, Copenhagen, where we could see big differences between different supermarkets. They were the same chain and everything, but we could see big differences between what customers were buying in different regions, and that gave big differences in the profiles. What have you seen when you look into this kind of things?
Actually, we had similar experience in Portugal, that we had two installations. So from the same, let's say, branch of supermarkets, but they had like one supermarket had twice power consumption, and of course both systems were different. One was a cascade CO2, the other was pure CO2, and this system that we talked was pure CO2. And actually, when we visited the site, we noticed that there were some issues with the system. I mean, it was running on low charge, so that can be one contributing factor. But there are a lot of things when dealing with data, because data is blind unless you analyze it properly. That there are a lot of things that can affect and can cloud your judgment if you just get to the conclusion based on what you see on the power consumption. So that's a danger that we should be aware of.
Yeah. Thank you, sir. Thank you very much for your nice presentation.
Thank you.
Alex, can I ask questions also?
Yes, sir.
I have interested, which solutions for improving energy efficiency do you recommend to the region, to the Middle Europe? For example, ejector, dry, wet, or so on. So which, to improve energy efficiency, which you recommend for the Middle Europe?
Yeah, I mean, just to answer shortly. I mean, in terms of CO2 system, and if the topic is transcritical CO2, we don't have it here in the data now, but we are working on another paper that we are trying to see how much efficiency gain that we get through ejectors, and we are doing second law efficiency analysis. And through that, we have seen that, for example, on liquid ejector, we were receiving something in the range of 13% second law improvement. And that's the best thing about second law, of course, is that it's not dependent on temperature and so on. So we are seeing that with CO2 transcritical ejector, payback time is very low. So that can be a good method to go.
Thank you very much for the answers. We need to move on to the next speaker, which is Corrado del Viola Carabellese. I'm sorry if it's not well pronounced.
No problem.
And Corrado is from Frascold in Milan, Italy. The floor is yours.
Good morning, everybody, and thanks, Chair, for the presentation. With the current work developed in collaboration with the University of Padua, it is presented the simulation and the monitoring of a CO2 plant for commercial refrigeration serving a supermarket located in northern Italy. First, I will give you a brief overview about this work with the purposes and objectives. I will later describe the monitor system and the alternative configuration that have been considered to improve its performances. A numerical model has been developed and validated with the field data of the monitor system and then used to run seasonal simulation. Finally, I will show the result of these simulations comparing the COPs of the different configurations. The purposes of this work are the experimental investigation of a CO2 refrigeration system, an all-in-one solution that integrates heat recovery, and the assessment of possible system improvements in both cold and warm climate to increase its performances. The objectives are the use of the field data obtained from the monitor system and use this field data to validate a numerical model and run seasonal simulation, also considering the system improvements. The configuration considered in this study is installed in a supermarket in northern Italy and located outside Milan. This benchmark configuration is a booster system with parallel compressors that meets the cooling demands at two different temperature levels, with evaporating temperature of -33 degrees Celsius and -9 degrees Celsius. The CO2 system feeds the hydronic circuits for sanitary hot water production, space heating, and air conditioning. An external evaporator is placed in the same framework of the gas cooler and at the same pressure level of the MT evaporators. It works during the winter time when the heat recovery is needed, absorbing a thermal heat flux from the outside and with no useful effect. This two-stage heat recovery requires the production of high-temperature water, and this may affect the performances of the system. Field measurements have been carried out to monitor The system and some results, such as the working condition of dry evaporators and the high pressure regulation, have been used to develop and validate the numerical model. Both figures show the 4 different pressure levels of the system. During the non-heating season, the high pressure is regulated based on the external air temperature, while during the coldest period, the system is forced to work in transcritical mode to increase the amount of heat available for space heating. Regarding evaporators and compressors, the figure on the right shows that as the external temperature increases, the LT consumption remains constant during the year, while the MT consumption proportionally increases. The external evaporator is enabled for temperature below 15 degrees Celsius, and its heat flow rate increases for lower external temperature, reaching a maximum at about 1 degree Celsius. The figure on the left shows that the highest energy consumption for the MT compressors is reached during the winter time due to the heat recovery request. In summertime, the energy consumption of both MT and auxiliary compressor strongly increase with the outdoor temperature due to the fact that larger amount of flash vapor is separated in the intermediate pressure receiver. Some alternative solutions have been analyzed to increase the performance of a benchmark configuration, the one of the monitor system, considering the climate data of 2 different cities, Bratislava and Athens. The first one is a booster system with parallel compression and overfed evaporators at both medium and low temperature levels. The liquid separated in the medium pressure receiver is expanded to the low pressure level, and an internal heat exchangers allow to avoid the liquid droplets at the compressor suction. In this case, overfed evaporators allow to increase the evaporating temperatures compared to dry expansion evaporators. The second configuration integrates overfed evaporators and vapor ejectors, which suck the vapor at the outlet of the medium pressure receiver and reject it at the intermediate pressure level, recovering part of the expansion work. The third and last configuration integrates overfed evaporators and a dedicated mechanical subcooling working with propane. The solutions allow to decrease the refrigerant temperature at the outlet of the gas cooler below the outdoor level, reducing the flash vapor separated in the intermediate pressure receiver. A steady-state model has been developed in MATLAB, and some results obtained from the monitoring of the system have been used as boundary condition. The number and type of compressor are the same of the monitor system. One compressor of each group is equipped with an external inverter with frequencies between 30 and 60 Hz. With the overfed evaporators, the evaporating temperature are increased by 5 Kelvin compared to dry expansion evaporators, and the vapor quality at the outlet equal to 0.95 has been considered. Both vapor ejectors and mechanical subcooling are enabled when the outdoor temperature is above 20 degrees Celsius. Each configuration previously described has been assessed using the climate data of Bratislava and Athens, obtained from Energy Plus and reported in the figure on the top right. The figure on the bottom left shows the specific thermal loads for Bratislava throughout the year, obtained considering the nominal capacity reported on the top left. In the specific case of the cooling capacities, a weekly load profile has been defined and a correction factor considered proportional to the external temperature. The simulation results of Bratislava show that overfed evaporators allow to bring benefits all year round, increasing the performances for all the outdoor temperature, thanks to higher evaporating temperature compared to dry expansion evaporators. The use of vapor rejectors help to further increase the performances in the summer period, but the benefits are low for Bratislava due to relatively low outdoor temperatures. The configuration with a dedicated mechanical subcooling is the one that brings more benefits and allow to achieve a higher COP during summertime compared to the winter period. Performances for Aten are generally lower compared to Bratislava due to higher outdoor temperature. In fact, the yearly average temperature for Athens is about 6.5 degrees Celsius higher. Vapor ejectors are more effective because they are enabled for a larger number of hours during the summer period, about 3,500 hours in Athens and for 1,500 hours in Bratislava. The mechanical subcooling sensibly increases the performances during the summer period, reaching a summer COP that is very close to the winter one. In conclusion, field measurements have been carried out to monitor the operating condition of a CO2 refrigeration system serving a supermarket located in northern Italy. The system meets the cooling demand of the supermarket and fits 3 hydronic circuits for sanitary hot water, space heating, and the air conditioning system. The data obtained from the monitoring have been used to validate a numerical model and simulate the performances of alternative solutions using the climate data of Bratislava and Athens. Overfed evaporators proved to be the most effective solution since they allow to reduce the energy consumption for all the outdoor temperature, with energy saving of 3.8% and 77.5% for Bratislava and Athens respectively. Vapor rejectors are effective for high outdoor temperature, and so they produce larger energy saving for Athens, 9.5%, compared to Bratislava, 4.1%, characterized by a milder climate. Mechanical subcooling is the most effective solution in summertime and allows to a reduction in the energy consumption of 4.5% and 9.7% from Bratislava and Athens respectively. Thank you very much for your attention.
So now I'm back in the system again. Thank you very much for a very nice presentation. And let's see if there's any questions here. Yes. Which simulation for improving energy efficiency do you recommend for the region close to Strasbourg?
Yeah, it could be analyzed the seasonal, maybe first the seasonal temperature. So it is very difficult to give an answer immediately because we have run for the case of Bratislava and Athens. We have decided to consider these two different cities because they have different climates. So in the case of climate, colder climate, similar to those of Bratislava, maybe it should be analyzed the specific temperature during the season. And for those solutions, maybe vapor ejectors, as we have seen, could bring less benefits compared to, for example, overfed evaporator first. So it depends on the specific city, the specific climate, also considering the changes in our climate globally, so it depends.
I think we can take the second one also. How can be defined conditions for applications of reactor, dry, wet?
In this case, we have in our work we have considered ejectors, vapor ejectors, so not liquid ejectors, and using also the overfed evaporator. So in our cases, we have used correlation from literature for the vapor ejectors, and in our case, they sucked the vapor outside the empty pressure receiver and recovering part of the expansion work.
Thank you very much for these answers, and I think we have to move on to the next presentation, which is field measurements and analysis of supermarket refrigeration low temperature units by Ivan Konstantinov, a postgrad teacher, but it doesn't mention here where, but you can introduce yourself. Thank you very much, sir. The floor is yours.
My topic is the experiment and analysis of commercial refrigeration units of low temperature. The authors are Mikhailo Khmelnyuk, Ivan Konstantinov, Valery Vozny. Introduction. The Kigali Amendment to the Montreal Protocol entered into force in January 2019 as a legally binding agreement aiming to phase down the production and use of HFC gases. With the Kigali Amendment, commercial refrigeration users will need to replace their cooling systems running on these gases, which opens the opportunity to replace these systems with modern ones. The experiment was carried out on the territory of the research site of Yuka Invest Ltd. For comparative analysis, a modification of the display freezer M200V was performed. Working in the direction of the development of refrigeration equipment, the most relevant issues are the preservation of the environment, the increase of energy efficiency, and the reduction in the cost of equipment itself. A number of experiments were carried out over pilot units, and detected temperatures have been validated. The experimental unit has been designed using specifications and guidelines, which can be consistently used to ensure efficient development of equipment. The obtained study results make it possible to determine the thermal fields for commercial refrigeration equipment, to determine the places of excessive thermal load, and the possibility to collect the basic data to start the creation of a universal model for developing the commercial refrigeration equipment. Recently, the refrigerant R404A has been widely used. Therefore, the transition to refrigerants which have lower GWP than R404A has should be done as a whole, taking into account all factors. R290 is being increasingly used, especially when there continue the research and development for improving the system performance. During these experiments, there have been performed the full analysis and comparison of three refrigeration agents, R404A, R452A, R290. Their thermal physical properties and power consumption at the same parameters of the refrigeration system. Main section. Supported by Yuka Invest Ltd. And Odessa National Academy of Food Technologies, a research stand was developed with the possibility of monitoring thermal and physical properties, changing operating modes, and analyzing the load of power supply network. You can see two pictures. One of them is experimental stand M200V. Number 1 is glass leads, 2 inner case, 3 body, 4 compressor bay, 5 grid of compressor compartment, 6 controller, 7 system management, 8 manometers, 9 network electric current analyzer, 10 condenser thermometer panel, 11 evaporator thermometer panel, 12 basic parameters panel. On the second picture, you can see the schematic diagram of systems. The system components are 1 compressor, 2 precondenser, 3 blower fan, 4 tube on sheet condenser, 5 filter dryer, 6 recuperative heat exchanger, 7 tube on sheet evaporator. Experiment parameters. The following refrigerants were filled into the refrigeration system in sequence: R404A, R452A, R290. And after setting the operating parameters, the refrigeration unit was connected to the power supply. During the experiments, the stand was configured to control the periodic operation of the blower fan of the precondenser and compressor. Blowing was carried out during system operation, and LED lighting was turned off to reduce heat and energy consumption. LED strip for lighting is an additional option, and according to ISO 239532 2005E, energy efficiency measurements are performed without it. The study was conducted in the laboratory at the research site in the third climate class. The equipment used for measurements and monitoring was checked in advance with certified analogs and calibrated. Each system test was performed for at least 24 hours. In accordance with the experiment procedure and commercial refrigeration equipment, all measurements were taken after the freezer went into operation. When measuring the power consumption, there have been taken manometer readings and thermal indicators of the refrigeration system, according to which the system operation schedule was built during the cycle. The following results were obtained at the end of experiment. You can see them on 3 different charts. Number 1 is graph of injection temperature change, 2 graph of compressor oil temperature change, 3 graph of change of temperature at the beginning of condensation, 4 graph of change of average value of temperature of the condenser, 5 graph of temperature change at the end of condensation, 6 graph of the change of suction temperature in the compressor, 7 graph of temperature change in the cooled volume, 8 graph of changes in the average value of evaporated temperatures. At the end of the period of each experiment, 24 hours, the readings of the network analyzer were taken. You can see them on 3 different pictures. These are the parameters of power consumption during 24 hours. The obtained energy consumption results fully correspond to the logical conclusions after the analysis of temperature indicators, manometer readings, and analytical experiments of thermophysical properties of the following refrigerants. Experiment results. During the experiments, experimental temperature and energy comparisons of different types of refrigerants were obtained. As a result of the analysis of the received indicators, the positive and negative factors of each of them are revealed. The main results of the experiment are listed in the summary table. Please see below. Conclusions. After analyzing the results obtained from the summary table, a histogram was constructed for visual analysis of key parameters. The conclusion of these studies to confirm the possibility of a complete transition to a natural analog with GWP equals 0. In parallel, there has been discovered the low energy efficiency of the analog of R404A. Although R452A is fully interchangeable with R404A without oil or compressor changes, it is not an energy-efficient refrigerant. In addition, R452A has a GWP equals 2141, indicating a ban on its use from 2022. Comparing the R290, its advantage in terms of energy efficiency and cost is obvious. The advantages of R290 also include its monogamy and therefore, as the experiment shows, and its equality, the temperature in the liquid phase, in the volume of the heat exchanger. However, its advantages in the transition include the need of oil change in the system and explosiveness. Another disadvantage of propan is the limitation of its amount in the system and the need to comply with safety standards during design and operation. R290 remains the most promising analog of R404A in low-temperature technology in the field of commercial refrigeration equipment. No significant problems have been identified in the replacement of refrigerants, and therefore, as experience shows, capillary refrigeration systems remain promising in the global refrigeration equipment market.
Thank you for your attention. I'm sorry for not being to introduce myself. I'm Ivan from Ukraine, Zhytomyr. I work at IIR Invest Ltd. and study at Odessa National Academy of Food Technology.
You had my presentation.
I'm sorry.
You watched my presentation.
You watched my presentation, analysis of commercial refrigerating units for low temperature. The experiment was carried out on the territory of research site of IIR Invest Ltd. Thank you.
Thank you very much, sir. Just a little quick questions, because I don't see any questions on Slido. Have you considered any of these new low GWP blends, means 454, 55, something like that?
Sorry, can you repeat? So thanks to the system of was put in, how it was protected for, як він захищає до системи 400 було вставлено 280 чи 280.
I guess it has to be 290.
Sorry.
It says here in the Slido questions 280. I guess it's 290. There's nothing called 280.
Як воно було захищено від не знаю, від чого, що він...
I'm sorry, 1 minute, please.
Here he asks, in the system was 404A or 404A, but if you put in propane instead of 404, how do you protect against sparks that can ignite the propane?
Не знаю, чесно. Я підвожу тебе, ну нічого не можу тягнути. Sorry for interruption, because we can't understand, because as you had and you see watch on the Ivan's presentation, that is to the system for R4 and 4A was put 219, yes, 90. And what do you mean for
how did you protect against fire from electrical sparks?
Yes.
Там была...
Что?
Сейчас. По-перше,
захиститися від
я зрозумів. Система є не ізольованою, а система є ізольованою, і заправка заповнення хладагенту там в табличці заправляє.
Де? Що?
Заправка в рамках дозволеного 75 грам, да.
Господи, як
там є в табличці воно. Не в тій. Там.
Давай нажимаємо. That is what? Оце?
Да.
Refrigerant?
Да.
Що це?
Заправка 75 грам в межах дозволеного. Да. Система є.
There were a refrigerant charge about 75 grams and what?
Система є ізольованою.
And the system is certificated and isolated.
Okay. I think it is enough. Thank you very much for your presentation. It was very interesting to hear. And the next presentation will be by Professor Peter Tomline, and it is about field measurements on a rooftop condensing unit before and after a reconstruction. Mr. Tomline, the floor is yours.
Dear friends, I will speak about field measurement on rooftop condensing unit before and after reconstruction. Firstly, about retrofit from AC to EC fans, then about hourly method for calculation heat demand, and finally about rooftop after reconstruction to be reversible. Behind is a cooling circuit as part of a ventilation unit, which was cooling conference room. Air handling unit has a recuperator and evaporator, and condensing unit with output 45 kilowatts has a wired body for the fan. On the top you can see AC motors, and beside is the same condensing unit with a plastic body for the fan with EC motors on the top. We have made measurement before and after retrofit using ClimaCheck analyzer. We have done it in two steps. Firstly with AC motors and after retrofit with EC motors. You can see now location of power analyzer, which is behind the condensing unit. Beside is the data transmission to the ClimaCheck website in front the PC, and on the right side there are power measurement of the compressors and fans. All the data were evaluated in pH diagrams, and we have made also comparison of SFP, specific fan power, at the same condensing pressure. Fan power measurement were done by protocol Modbus and by PowerScout. These data from PowerScout have better corresponded with producer data, and that's why they were used for the next calculation of SFP. Specific fan power of EC fan was 2.5 lower at the same condensing pressure as for fan with AC motor. Measurement at the different condensing pressure at the same outside temperature. You can see adjustment of condensing pressure from the maximum pressure 17.8 bars up to 16.9 bars. At this pressure difference, we have reached savings by decreasing condensing pressure in watts, 200 watts. Ideal cooling circuit is when the condensing pressure is decreasing, then evaporating pressure should be on the same level, or the better, it should increase also. But it was not possible because we had the on-off compressors, and if the condensing pressure was decreasing, then also evaporating pressure was decreasing, and it means that temperature lift was increasing too. In this operation, we had reached a little bit better energy efficiency, but the cooling output was decreasing. Energetical and ecological assessment. At the pressure difference of condensing pressure 1 bar, total compressor and fan power input has decreased at about 200 watts, but at the same time the cooling capacity has decreased because decreasing of evaporating temperature. So, how to reach higher savings? We have made several economical assessment of fan retrofit, but the basic problem was the short operation time, because this rooftop has cooled only conference room, and economy is dependent on hours of operation and size of AC fans. So the decision was measurement on rooftop after reconstruction to be reversible. Firstly, we have made a calculation of building energy demands for also heating mode. We have used hourly and monthly method for calculation heat demands. When we used monthly method, this is this yellow line, it means we have used the same temperature during all the months, during the night, during the day, and it means the energy demand was the same during every hour during the month. But if we used specific temperature for every hour, specific energy efficiency expressed by COP for every hour during the day, during the night, then you can see that the energy demand were different during the night, during the day, and the energy demand was calculated lower. And this hourly method has revealed also the need for cooling during the lunch time. So here is the comparison of hourly and monthly method for city Urbanovo in the South Slovakia. You can see that the hourly method has revealed need for cooling already in April, and monthly method only in June, when there was no need for heating. Monthly method has calculated higher energy demand for heating, as hourly method the difference was from 15 up to 20%. We wanted all the year operation. We have considered 4 reversible refrigeration circuits with and without refrigerant receiver, and we had possibility to measure on the cooling circuit with 2 bypassed thermostatic expansion valves. Here is the scheme of the rooftop with duo compressors after retrofit to be reversible. You can see duo compressors, on-off compressors, accumulator, 2 thermostatic expansion valves which were bypassed, 2 distributors, and so on. And you can also see location of all sensors which are connected with power analyzer with the software ClimaCheck. Suction and discharge compressor temperature after start of on-off compressor decreased after defrosting in the heating mode. You can see the suction temperature at the compressor, which has decreased at the start in heating mode after defrosting, and you can see a quick decrease of discharge temperature. So likely there was wet start. Here you can see the period of such measuring with possibly or likely wet start, which was ended by erratic oscillation of evaporating temperature, superheating, condensing temperature, and so on. And this this period was ended by the low pressure control, which switched off the compressors. Here is the next period of measuring, which was started only with one compressor, and by the end, the next or second compressor was switched on, and the evaporating temperature has decreased immediately, and the condensing temperature has increased, and this operation was switched off again with low pressure control. Important for reconstruction. Important is to follow temperature. For example, sun heating of evaporator in the morning can push refrigerant from evaporator into colder accumulator. After defrosting, thermostatic expansion valve is open while getting colder. Attention should be paid to compressors, axial and radial degree of freedom, control against possibly risky on-off compressors operation, accumulator capacity, pressure losses, long tubes, clean needs, possibility of refrigerant receiver, pump down, and so on. Conclusions. Rooftop originally operated with fans with AC motors has been retrofitted to fans with EC motors. Field measurement proved higher efficiency after fans retrofit, even with on-off compressors. Economy of fan retrofit depends on operation time, which in cooling mode is short. We have decided to examine reconstruction on reversible cycle to prolong operation. Used hourly method had calculated lower energy demand for heating mode, and so in this way hourly method has not supported economy of the rooftop retrofit and reconstruction. Rooftop reconstruction from only cooling mode to also heating mode enables longer operation time and expected better retrofit economy. Success of reconstruction from only cooling mode to also heating mode depends on the possible extent of reconstruction. Field measurement proved necessary precautions against possibly risky on-off compressors operation. This work and experimental measurements were supported by Slovak University of Technology and Slovak Association for Refrigeration, Air Conditioning and Heat Pumps. Thank you for your attention.
Thank you very much for this very interesting presentation. There is a couple of questions here on the Slido. Why have you used hourly method if it was not supportive or for longer operation of cooling circuit? You are muted, sir.
Okay. Hourly method is a very promising method because and it should be used for calculation building demands, heat demands, because mostly where heat pumps and photovoltaic panels are installed, because the heat demands are calculated more precisely, and we calculate less energy demand. It means that the building will be shifted to the higher, to the better energy class of building. It means among building nearly zero energy buildings. So that's the very important reason, because if we use heat pump, we can shift such building immediately to the class of nearly zero energy buildings. So it is important method, and it is a method for the future. This time we use this monthly method, but it is only because we do not have software for this hourly method. So it was very workable and to use this hourly method. But the software is developing. So I think during 1 year we will have software for calculation according to the hourly method.
And the second question is, do you recommend retrofit with AC motors to fans with EC motors?
Yes, the economy is not always the main reason if we think about the retrofit, because if the fan is at the end of this technical life, and then we should change for this fan with EC motor, because this old fan with AC motor is already not according eco design and so on, and we can have problem with spare parts. So that's why the economy is not the main reason for retrofit of the fan.
Thank you. I have one more question for you. I noticed that you don't use the de-superheater possibility in the heater, and in the summer you had very low heat need for space heating. But what about heating what you call it tap water for cleaning and for washing? Have you considered that as a measure to recover some of the heat that you actually produce when you are cooling?
Yes, it can be maybe, but this was rooftop only designed only for cooling, and it cooled only this conference room, so the economy was very problematic. But to reconstruct such a circuit also for heating the water and so sanitary water and something like that, it is. We had problem also with this reconstruction, and it was not successful, as you could see.
Okay, thank you very much. This, if you have any questions to all the other presenters of this, then we have a little bit of time, but there seems to be no questions at the moment. Otherwise, there will be a break now, as I think this next, it will be the invited papers that start at 1300 hours. You can see on the lobby that will be 2 papers on hydrogen, which is a very interesting technology. It seems we get a longer lunch break. So thank you very much to all our presenters this morning, and have a good lunch break. Thank you very much.